Okay, so we're now going to move on to the topic of reduction and oxidation half reactions, which again are kind of exactly what they sound like, right? So they are half of a reaction. That's why they call them half reactions. Okay, so it's one half of a reduction oxidation reaction. So as we know, there's two parts to a reduction oxidation reaction, right? There's the reduction part and the oxidation part. So no surprise here, a half reaction shows either the reduction part or the oxidation part, okay? What is different then? Um, well, besides that it only shows half, it also includes the electrons, okay? So that's where it really differs from just writing the whole reaction, is that now we're gonna actually look at what the electrons are doing, okay? So as always, in a reduction half reaction, an element gains electrons. Why? It's a reduction half reaction, right? So we have GR, right? Gaining electrons is reduction, GR, okay? So it gains electrons and therefore becomes more negative. Gains electrons, more negative. How do we represent that with a reaction? Well, I think of a half reaction as kind of telling the story of what happened to just one character in a reaction, right? A whole reaction tells a story. A half reaction just says what happened to this character, okay? So when we talk about characters, we're really talking about chemicals, right, or elements, okay? So in a reduction half reaction, what's the story? Well, it started out without electrons, right? It didn't have the electrons in it. So before the reaction, okay, the electrons in the element are shown as separated from each other. So you can actually look and see both of them. They're two different things. They're not together as one, okay? So to show that, we would say, we would draw, I'm just going to write my before side. Let's think of an example of a reduction half reaction. Well, we could say that you might start out with something. If something's going to be reduced, let's say, what about sodium? So if it was going to get reduced, it would be starting as part of a compound, right? It would have a charge that was going to be reduced. So you might have Na plus AQ. Again, the AQ means aqueous. It means it's dissolved in solution because that's how you would get an ionic compound. So maybe we dissolved some sodium chloride or something in a solution. So we have Na plus aqueous. Okay, so this is our before part. Before, it's separated from its electrons. So you can actually see it as separate from its electrons. So it's Na plus, and how many electrons would sodium gain to get reduced? Well, it would gain one to become neutral sodium, right? It wouldn't gain more than one and become negative. That would never happen. It would either be its ion charge of +1 or it would be its atom charge of 0. So there's kind of the before. See how they're separate? We've got a sodium ion and we've got an electron, but they're two different things. They're not together yet. But then after the reaction, right, they have merged together. So what would we say? We would say that sodium met up with this electron and now it's stuck inside of it. So now you can't see the electron anymore. It's there, but now it's in this thing, right? That's how sodium went from being a positive ion, Na plus, to just a neutral atom, just Na, right? Just a sodium atom, okay? So that is a reduction half reaction. That's the story of what would happen if sodium were to react with something else and end up reduced, okay? We can also write an oxidation half reaction. So let's say sodium got reduced, but maybe potassium was the other half of the story. So we might have had potassium, okay? And if it was going to get oxidized, right? If it was going to get oxidized, it would be a neutral potassium atom. Remember, it's going to lose electrons. In an oxidation reaction, it loses electrons, okay? So oxidation, Leo. An oxidation half reaction, an element loses electrons and becomes less negative. So we got to make this become less negative. So once again, before the reaction, now it's in reverse. Before the reaction, the electrons in the element are together. So how do we show that? Well, we just say, okay, there's an electron in there. That's why it's neutral, right? But after the reaction, they have been separated from each other. So after the reaction, they're separate. So how do we show that? Okay, goes from, if it's going to get oxidized, it's going to lose its electron to become whatever charge it has as an ion. If you look on your periodic table, you'll notice that potassium has a charge of K plus. Okay, and since it's an ion now, it would be aqueous. It would be dissolved in solution, probably, is where we would do this type of reaction. Okay, how did it get to be K plus? It lost an electron. So I kind of think of it as it fell off or it flew out, right? And then what happened to this electron? Well, it went, and if this is the other part of our half reaction, this electron and this electron are actually the same electron, okay? Because which electron did sodium gain? Well, the same one that potassium lost, right? So these are the same electron. Whatever potassium lost, sodium gained. So it's the same electron, okay? If these are part of the same full reaction. Put these together, what do you have? You have a full reduction oxidation reaction, or a redox reaction, right? Here's the reduction part, here's the oxidation part, and put them together, you got a redox reaction. Okay, so let's look at what this actually looks like in a full reaction, right? Because this is what you usually be given, and it'd say, what's the oxidation story here? What's the story of whatever's being oxidized? What's the story of whatever's being reduced? Okay, so take the whole story and pick apart just what's happening to individual characters. Okay, so I didn't leave myself much room. I'm going to write in below. Okay, so here we have gold, solid gold, okay, just a gold atom. And now we know all atoms have the same charge, and that charge is 0, right? And then we have the next kind of character here is sodium chloride. So, or sorry, sodium. This is silver chloride, right? Now, this is part of a compound, an ionic compound. So if you're following along page 6, 7, your periodic table, like you should be, you'll notice that when silver is part of an ionic compound, it has a charge of +1. Now, chlorine, when it's part of an ionic compound, always has the same charge. It's always -1. Okay. Now, what happened after? Well, after, gold is no longer alone. Gold is now part of an ionic compound, so it's going to have its ionic charge. Now, gold has 2 charges listed on the periodic table. It has Au1 plus and Au3 plus. We're not exactly sure what it would be until we look at, hey, it's with 1 chlorine. 1 chlorine is doing the job of balancing this whole thing. We know chlorine's charge is -1 or 1 minus, right? Well, that means if only 1 gold canceled out with 1 chlorine, gold's charge must just be 1 plus, right? So that 1 plus and 1 minus for 0 overall, okay? Because remember, all compounds bond so that they have a neutral overall charge. That's from science 10, right? But you can even tell this doesn't have a charge listed. This doesn't have a charge listed. Yes, both things are charged, but overall, AuCl is not charged. Even though Au is charged and Cl is charged, they have the opposite charge, and so they cancel out. Okay, now silver, what's happened to silver after? Well, it's alone now, right? And it's just an atom. There's no charge listed there. So that has a charge of 0 now. Okay, so to write the oxidation half reaction, first we got to figure out what was oxidized. Okay, and whatever was oxidized will have gotten less negative, right? Or more positive. Okay, although we don't like to say positive because we're always talking about electrons and they're negative. So if we look at gold, it went from 0 to 1 plus, right? 0 to 1 plus. So that is getting away from the negative numbers, right? Going from 0 to 1 plus, that's going away from the negative numbers down here and towards the positive numbers up here. So it's getting less negative. Okay, to get less negative, you have to lose electrons. And as we know, losing electrons, Leo, is oxidation. So the thing that was oxidized is gold. Now we got to figure out, how did gold do this? What actually happened with the electrons? What's the story of gold? Okay, the oxidation half reaction, in other words. Well, if I'm gold, I went from being solid gold. I'm going to do it a bit different. I'm just going to say I went from solid gold, and we know gold went from being just neutral, plain old gold, to being Au1 plus, right? Okay. Now, where do the electrons belong here? Did gold end up with its electron, or did it lose its electron? In other words, so did gold end up with its electron a part of it, or did it split up from its electron so that now you can kind of see them as 2 separate things? Well, it lost its electron, so now they're 2 separate things, right? Here it had its electron. After it became gold plus and it lost its electron, it was a separate thing from it, right? So that would be the oxidation half reaction. What's the reduction half reaction? Well, if we look at chlorine, it's not going to be chlorine because chlorine went from -1 to -1. So what would we call that? What would we call chlorine here? And if you said spectator ion, you're dead on because it's there, but it's not actually part of the redox, right? It's there, just spectating. Okay, but silver, on the other hand, went from +1 to 0. Hey, +1 to 0, +1 to 0. That's going this way towards the negative. So that thing is getting more negative. To get more negative, you have to gain negative electrons, right? You got to get more negative electrons to get more negative. So gaining electrons, reduction. Okay, so what happened to silver? Silver went from being an ion, Ag plus, okay? What did it end up as? It ended up as plain old silver, okay? Now we got to think, at which point is it before or is it after that it has the electron? That the electron is kind of part of it. It's grabbed it, right? Well, it's after, right? Because it gained that electron. That means before they were separate, but then it kind of picked it up along the way and ended up with it as part of it, right? Think of this as looking at two people from far away, or maybe a parent and their kid from far away. From far away, they could look like two separate people if they're separated, but once the parent picks up the kid, you could kind of, from far away, they would just look like one kind of blob off in the distance, right? Kind of sort of one person. So that's the idea here. They start out separate. You can clearly say, hey, there's a silver and there's an electron, but after, the electron is part of the silver atom, so it is no longer something you can see. So here, the electron falls off so that they end up separate. Here, the electron was separate in the beginning, and they end up together. Now, don't forget, what's this electron and this electron? It's the same electron, right? This one that gold lost is the same one that silver picked up, okay? Uh, Pop quiz from yesterday's topic, right? What would we call gold in terms of agents here? What is it doing? Well, it's oxidizing. So what's it helping something else do? It's helping silver reduce. So we would call gold, even though it's oxidizing, that makes it the reducing agent. Okay. Same thing over here. This silver is reducing. So what kind of agent is it? It's an oxidizing agent, right? It's not oxidizing, but by gaining this electron, it's helping gold oxidize, right? By taking that electron, it's helping gold lose its electron. Okay. One thing I want to point out before we move on, there's another way to kind of think about where the electrons go. So yes, there's thinking of the story that's being told, but sometimes that can get a little tricky and can kind of trip you up in your head a bit. There's another way to check if you've done it right. Okay, so there's a law that we've not really talked about, but it's always kind of been there in the background of our chemistry, and that's something called the law of conservation of charge. So you've heard of other conservation laws before. For sure, you've heard of the law of conservation of energy. You've definitely heard of the law of conservation of mass. They all say the same thing, right? The law of conservation of energy says energy cannot be created or destroyed, but it could change forms, right? Same thing goes here. Well, we did the law of conservation of momentum too, right? In our physics unit. So same thing there. Momentum could not be created or destroyed, but it could change where it was. That's what's happening here. So the law of conservation of charge, notice over here on this side, on this before side, what's the overall charge? Well, it's 0, right? There's only one thing here and it has no charge. That means on the other side, it has to be the same thing. And look, over here, we have a +1 and we have a -1. So overall, what's the whole side of this charge? Or sorry, whole charge of this side? It's 0. +1 and -1, that's 0. Good. So we put the electron on the right side, okay? Imagine for a second in your head, we had accidentally put it over here, okay? Let's just maybe picture that, okay? I'll do this and I'll undo it. What if we had accidentally put the electron over here instead by accident? Well, now we would go back to check our work and we would say, okay, the charge of this side is now -1 because we have a -1 and a 0. So overall, that's just -1. And then over here, we have a charge of +1. Uh-oh, we must have made a mistake, right? So we go back and we'll say, okay, whoops, I must have thought about this wrong, and then go, oh, right, okay, it's losing its electron, so it ends up separated from it, and then we have +1, -1, and 0. Okay, same thing goes over here. The charge of this side, +1, -1 for 0, and then the charge over here, 0. Good, so the charge is the same before and after. Okay, let's try one more example with these half reactions here. So here we have FeBr2 plus Pb, okay? That's our before, okay? So let's take a look at each one. Now, iron, Fe, okay, iron, kind of a weird name, comes from the Latin name for iron, but we see that on our periodic table, you'll notice iron has 2 charges listed. It has 3 plus or 2 plus. So which one is it here? Well, to answer that, we have to look at what it's paired up with. It's paired up with bromine, okay, Br. And how many what's the charge of bromine always? Bromine's charge doesn't change. It only ever has 1. Same with all nonmetals. Okay, bromine only ever has a charge of 1 minus when it's in a part of the compound, right? If it's by itself, it would be 0. But here it's part of an ionic compound, so it has a charge of 1 minus. Now, there's 2 bromines, right? It's 2 bromines, each with a charge of -1. So what does the charge of iron have to be? There's only 1 iron. So what charge does it have to perfectly cancel with the 2 minuses that are coming from the 2 bromines that each have a charge of 1 minus? Well, the charge of that iron to cancel out with 2 1 minuses must be 1, 2 plus, right? 1, 2 plus and 2, 1 minuses for an overall of 0. Okay, now we look at lead, Pb, all by itself. Hey, that's just a lonely atom. We know the charge of that. That never changes, 0. Okay. Now, lead is another one with 2 charges listed, but we kind of know now, right? Bromine, if there's 2 of those minus 1s, if there's 2 of those minus 1s from the bromine, and there's only 1 lead, and it cancels that out, this would not be lead 4 plus, like is listed on the periodic table. It would be the other one. It would be lead 2 plus. So this must be lead 2 plus. So it has a charge there of 2 plus. And then poor lonely iron all by itself, okay, now has a charge of 0 because it's a neutral atom. Okay, so the oxidation half reaction. To figure out the oxidation half reaction, we got to decide who here was oxidized. So looking at it, okay, I'll give you a sec. This would normally be like a whiteboard question. So actually maybe pause the video and see if you can work out the oxidation half reaction on your own and the reduction half reaction on your own. Okay, and then when you're done, you can press play and see if I got the same thing as you, or skip ahead to my answer if you're not interested in hearing me blab about it. Okay, but I'm looking here and I'm saying, okay, if it got oxidized, right? If it got oxidized, Leo, it lost electrons. If it got reduced, whoops, if it got reduced, it gained electrons, grr. So when I'm looking, okay, so if it lost electrons, it has to get less negative. So what here got less negative? Well, iron went from 2 plus to 0. That's getting more negative. So it's not iron. Bromine went from 1 minus to 1 minus. That's not even changing. So that must be the spectator ion. But lead, lead went from 0 to 2 plus. Hey, that is getting less negative, right? That's going on a number line. If these are our positives, these are our negatives. That is going away from the negatives. To go from 0 to 2 plus, right? 2 plus being over here somewhere, that's getting less negative. So lead must be getting oxidized. It's losing those negative electrons. So let's start writing our oxidation half reaction. I'm going to approach this one a bit different. I'm just going to do it purely from a sense of conservation of charge. I'm not going to worry too much about the story, although it's good to understand it both ways. So what do I know happened to lead? First of all, lead went from solid, regular lead to charged lead, right? A lead ion. And if it's an ion, it'll be aqueous in solution. That's how we kind of get the ions. Okay, now if lead went from solid to 2 plus, over here the charge is 0. Over here the charge is 2 plus, right? I'm only allowed to add in negative electrons. So if I put them here, okay, this is wrong, but if I put them there, that's bad, that's worse, right? Now I've made this side 2 negative, this side 2 plus. That's not what I wanted. I wanted to make the charge be the same before as it was after. So that's no good. Okay, take that back, undo, undo, whoops. Okay, now over here, if this is 2 plus, hey, I could add 2 negative electrons. And there we go. I have 0 on this side. Whoops, I don't even need a plus, I guess. I have 0 overall on this side, and then on this side I have 2 plus from the lead, and then 2 minus from the 2 electrons. Each electron has a charge of -1, and there's 2 of them. So 2 minus, 2 plus, for overall, this side has a charge of 0 now. Okay, great. Now, I kind of skipped over that. Why 2 electrons? Well, how many electrons do you think lead had to lose to go from 0 to 2 plus, right? If each electron has a charge of -1, then this thing must have lost 2 electrons, right? So that's why this thing here is 2 electrons. Okay, what about the reduction half reaction? We already said bromine would be the spectator ion. So by process of elimination, we must be dealing with iron here. So again, I'm going to kind of do it a little differently than I did the last one. Either way is fine. In fact, both are kind of what I do on each problem. I check my work with the charge balancing method after I think about it and tell the story first. By story, I mean what happened to this element in this reaction. Iron went from Fe2 plus, and notice it was aqueous. Okay, it went from Fe2 plus. Okay, it ended up as FeS, solid iron. Okay, and now I'm going to ask myself, where do the electrons go? Where do they belong in this reaction? Well, if I put them here, this side's going to get more negative. I'm going to have plus, I'm going to have 2 minus on this side, right? And I'm trying to make it equal, or I'm trying to make both sides equal, and I only have negatives that I can use. So if this side's 0, this side's 2 plus, and I only have negatives to work with, I need to bring this side down to 0. So I'll add 2 electrons. There we go. And that checks out with my story too, right? Remember, what happened to iron? Iron started out separate from its electrons, and then it gained them, it reduced, so that it ended up together. They're now one. They're right. They're living together, the electrons and the iron. Same thing over here. What happened to lead? It started out with its electrons, but then they kind of broke off, right? They split up. And I'll remind you one more time, okay? Those two electrons are not just two random electrons, they're the same electrons. That goes for the last example too. Goes for every example, okay? It's not just two random electrons, there's the same two electrons. So think back to what we were saying about for something to be oxidized, something else must be reduced, okay? So here's a hint for you. If you ever find that your oxidation half reaction and your reduction half reaction have a different number of electrons, something went wrong, okay? Often the way to fix it is to go back and look and see if there were any coefficients there, okay? And then you just kind of add them in. For example, this is not true, but if it had been, let's say to balance this equation, it had been, and you don't need to balance in Science 20, but you might be given a balanced equation already. Let's say this had been, instead of FeBr2, I'm just making these numbers up. This is not going to be balanced. I'm just trying to show you what I mean. Okay, if we had 2 FeBr2 makes 2 PBr2, okay, PBBr2, I should say. Okay, what if that were the case? Then we would just fix it by saying, okay, well, 2 irons, actually, I should really do this. Let's just say there were 2s everywhere, okay? Which technically, if we had balanced it this way, I would divide everything and get just 1s, but again, we don't need to worry too much about that. What would I do? I would say, well, 2 irons became 2 irons. 2 iron 2 pluses became 2 irons. So 2 iron 2 pluses became 2 irons. And then in that case, how many electrons do you think would be transferred? Well, it wouldn't be 2 anymore because 2 irons each gain 2 electrons. So 2 times 2, right? That's 4. You would essentially find the base reaction and then multiply everything by the coefficient that belongs there. Same would go for lead, right? Now 2 leads became 2 lead 2 pluses. So 2 leads became 2 lead 2 pluses. How did they do that? By losing 4 electrons. Each one lost 2 for a total of 4 electrons. Okay, so I want to be clear. I'm just throwing this in there so you know how to deal with coefficients when they do pop up. Those coefficients do not really belong in this problem. Definitely now you can get a good start on that formative practice assignment.